Hello, everyone, and thank you for tuning in. My name is Vikas Aragam. I am a PhD student at the University of Texas at Austin, and today I'll talk about some work I've done on how multi-field inflation in supergravity appears to be rare and tachyonic. This work is based off of this paper that came out late last year and was done in collaboration with my co-authors, all of whom are listed right here. So as the title suggests, this is primarily a talk about inflation, which is our best theory to explain various early universe phenomena and current observations, such as the large-scale uniformity and anisotropies of the CMB and large-scale structure. And the simplest models of inflation consist of a single scalar field that slowly rolls down a nearly flat potential. And even this simple setup actually manages to accomplish a lot. So one can naturally ask, why should I care about multi-field inflation? After all, single field models can have good phenomenology and even some motivations from the UV. The thing is, when we actually look at UV theories, we tend to find lots of scalar degrees of freedom. And this is frequently the case in supergravity and in string compactifications. We often find steep potentials in tachyonic directions in these theories, which has led to various swampland conjectures. And because the scalars are typically light, we can't simply integrate them out. And that forces us to try and realize inflation amidst all these complicated multi-field dynamics. So to do this, we can start by thinking about a theory consisting of n real scalar fields with an Einstein frame action given as such, where the main thing I'd like to point out is that the kinetic term for the scalars includes the possibility of a metric on the space of fields, coefficients multiplying each derivative term, which can be written covariantly as such. This metric is not the same as the space-time metric, but it does give rise to some interesting possibilities. When we get the equations of motion from this action, we obtain a Friedmann equation for the scalars and their potential, and Klein-Gordon equations for the scalars consisting of the usual Hubble friction term, but also a field space covariant time derivative, which includes Christoffel symbols computed from the field space metric. Now, we ultimately want to solve these equations of motion, and the solutions can be visualized quite nicely as spanning a trajectory in the space of fields. And as with any trajectory, we can write down a unit tangent vector given by the normalized field velocities. And because we ultimately want inflation, that is a slowly varying Hubble parameter to source exponential expansion, we will demand slow roll along this tangent direction, meaning that the slow roll parameter epsilon using the equations of motion can be expressed in terms of the derivative of the potential along this tangent direction. And this parameter must be less than 1 for inflation. Additionally, we can define a unit normal vector, which is orthogonal to t and runs along the direction of its time derivative. And the norm of this time derivative is what we will call omega, the turning rate, which characterizes how quickly the trajectory curves in field space. We're going to think of this turning rate as large when it is of order 1 in Hubble units. And this actually corresponds to non-geodesic motion in the field space, as opposed to effectively single field dynamics being purely along a geodesic direction. So turning is actually what allows for inflation in the steep potential gradients that we often see in UV theories, which serves as another motivation to think about multi-field inflation specifically. But of course, these are theoretical motivations. Phenomenologically, turning is also useful because it's actually what couples the adiabatic and entropic modes of inflationary perturbations. And this coupling can give rise to unique signatures in the primordial power spectrum, such as large power at high wave numbers, giving rise to the production of primordial black holes, and even a stochastic gravitational wave background. So really, turning kind of goes hand in hand with multi-field inflation because it is indicative of genuinely multi-field dynamics and phenomenology. So with those motivations, now let's just take a quick primer at understanding what inflation looks like with two scalar fields. We'll choose a basis of fields consisting of one field R, which we're going to think of as a saxion, and another field theta, which we'll think of as an axion in anticipation of looking at supergravity down the road. We'll parameterize the field space metric as a factor f squared of R times the Euclidean metric on field space. And this might seem restrictive at first, but this is actually equivalent to many other forms of the field space metric under a suitable coordinate transformation. Under these, within this setup, we can then write down the equations of motion of the fields R and theta, and they look about how equations of motion should look with acceleration terms, some velocities, and crucially, terms coming from the Christoffel symbols of the field space metric, the derivatives of f. Primes here denote e-fold derivatives, 1 over h d dt. And now we'd like to understand the solutions to these equations. Just as a starting point, let's think about solutions in which the theta field is constant and r varies. These actually correspond to geodesic motion in the field space. So saxion inflation is effectively single field. So for genuine multi-field dynamics, we really need motion in the axion direction theta. So for analytic simplicity, let's take r to be constant, allow theta to vary, and this is what we'll call multi-field axion inflation. And when we impose slow roll in the theta direction, the equations of motion simplify quite drastically. And this assumption, again, might seem restrictive, but it does encompass a broad class of models in the literature. And in some of the numerical work I'll describe a little bit later, we do allow r to vary. These equations of motion ultimately must be consistent with each other, and demanding that yields a consistency condition, which is purely a function of the potential, its derivatives, and the metric factor, which means that this condition is actually independent of initial conditions. So we can use this to check across an entire field space for a given model what regions are both slow roll and high turning allowed. Just as a proof of concept, here we have plotted on the left an inflationary potential from a supergravity model constructed by Ellis and company. And the inflationary solution that they found, the trajectory, is plotted in red. On the right side, we have plotted the contours of this potential. And these red lines correspond to the regions where the consistency condition is satisfied. And as we can see, one of these red lines looks exactly like the inflationary trajectory. And this was done without evolving the equations of motion at all. So this is already a check to see where can we look for inflation in these complicated field spaces and even recover previously known solutions. Now, under these assumptions, we can write down the unit tangent and normal vectors as such. And then we can compute the slow roll parameters, epsilon and omega, which are given in terms of derivatives of the potential and the field space metric factor. So these, again, don't care about initial conditions, so we can compute them globally across an entire field space for any model and see where do we get slow roll and high turning. One last thing we're going to need are an understanding of the multiple fields masses, which are contained inside this mass matrix given by the covariant Hessian of the scalar potential. And in slow roll, we can express two of these elements in terms of the turning rate parameter. The eigenvalues of this matrix, what we're going to think of as the field masses. And under the slow roll assumption, all of these eigenvalues can be shown to be positive if this last element Vn is larger than 9h squared. However, when this element is smaller than 9h squared, that means there's at least one tachyonic mass, which has some interesting theoretical motivations, but also can give rise to an exponential growth in the primordial power spectrum, which leads to some of the rich phenomenology that I described earlier. So now that we've set the stage, we'd like to really understand how does multi-field inflation fit into fundamental physics? And in particular, we're going to look at supergravity with it being a low energy effective description of various string theories. When we take a string theory and compactify down to d = 4, we get many complex scalars. So we'd like to understand, what does inflation look like in this complex, literally complex field space? To do so, let's lay out a few basic ingredients of supergravity. In d = 4 with complex superfields capital phi I, we can write down an axion which has an Einstein-Hilbert term, a potential for the scalars, and a kinetic term with the field derivatives interproducted against the Kähler metric on the complex field space. The Kähler metric is the Hessian of the Kähler potential, and the other ingredient, the scalar potential, is given as a function of the superpotential, a holomorphic function of the complex superfields, and its Kähler covariant derivative, defined as such. We're not going to need these too much, just needed to flash them briefly. Now, one of these superfields we're going to think of as the inflaton superfield, which will decompose into real and imaginary parts. And when we impose multi-field axion inflation, with R being roughly constant and theta varying, we can then write down the slow roll and turning parameters, epsilon and omega, purely in terms of the supergravity potential's derivatives and the Kähler metric and its derivatives. And these can be computed globally, no initial conditions necessary. So with those tools, let's take a look at a concrete model. The first one that we looked at was one inspired by no-scale supergravity, with a Kähler potential given as such, and a superpotential given by a second superfield S times a holomorphic function F. We're going to think of phi as the inflaton superfield and S as a Goldstino. And even though we have this Goldstino floating around, we're going to be able to set it to 0 in the potential by enforcing a nilpotent condition. Now, this function F that I mentioned actually doesn't need to be of any specific form for inflation. Many different forms allow for inflation, although I will talk about a concrete case in just a sec. And this parameter alpha here, when it's equal to 1, is exactly the no-scale supergravity model, and we allow it to be deformed because it has an interesting connection to the curvature of the field space, which goes as -1/alpha, which we'll see gives rise to some interesting red flags in just a bit. So let's take F to be of this form, a constant plus a monomial in the inflaton superfield. And when we write the potential in the field space metric in terms of the real fields R and theta, they look of these forms. Specific forms aren't super important, but what is important is the turning rate that we get from this, which goes as root epsilon over root alpha. Now we know epsilon needs to be small for inflation. So in order for omega to be large, we need alpha to be quite small, which, as we just saw, when alpha is small, gives rise to a large field space curvature. So already this is telling us that in order to have high turning, genuine multi-field dynamics, we need small alpha and large field space curvature, which is actually known to be a bit difficult to construct in perturbative string theory. So that's already a sign that multi-field inflation in supergravity is a bit rare, to say the least. We can also look at the mass matrix element, VNN, which is actually negative definite in this limit. And what that means is that it is smaller than 9/8 squared, implying the existence of a tachyonic mass along the trajectory. Just to show some figures, on the left, I've plotted the turning rate of a given inflationary solution as a function of time, or e-folds. And for different values of alpha, we see that we can actually modify the turning rate. And if we push alpha to be too large, we no longer get enough inflation to explain, observations. So alpha does need to be pretty small from an observational and from a turning rate perspective. On the right-hand side, I've plotted the minimum eigenvalue of the mass matrix, which for all values of alpha is, as promised, distinctly negative, meaning that there is a tachyonic mass for this inflationary solution. Now, just to quickly show a few other models that we looked at, one of which we've called the EGNO model, which was constructed by Ellis and co-authors in this paper. The same potential that I showed in the plot earlier. And it comes from, it consists of this scalar potential and a superpotential of the same form we saw before, but with a function f specified a bit differently. And with this supergravity construction, we were able to repeat the same analysis and find almost the same story as before. We can get long-lasting inflation with small epsilon, order 1 turning, so long as alpha is less than or roughly given by 1. And again, this corresponds to a large field space curvature, this time positive, still potentially problematic in perturbative string theory. And additionally, we still have a tachyonic mass along the trajectory. So we've seen the same thing in these two different models, but this was all done analytically. To get a broader sense of what's going on in the supergravity landscape, we took a look at 13 other models using a numerical scan over the field and parameter space of these models. This code was mainly done by my collaborator, Robert Rosati. You can find it in his GitHub page. And the code evaluates and evolves the equations of motion while minimizing a cost function, which attempts to maximize the number of e-folds, the turning rate, and minimize the slow roll parameter epsilon. We also allow this axion to evolve in time, but this had no meaningful impact on the results. And what we found is that none of these models supported long-lasting, sustained turning. Some of them did have effectively single field dynamics with small epsilon over 60 or more e-folds, but none of them had sustained turning. So most of them looked single field in nature. So I think that brings us to our summary. In conclusion, we've seen that multi-field inflation is motivated from fundamental physics, and that the dynamics and phenomenology of multi-field go hand in hand with large turning rates. And in our analytical and numerical analyses, we find that supergravity very rarely yields slow roll, high turning inflation. But when it does happen, we tend to have tachyonic masses with interesting phenomenology and theoretical motivations. But the price that we pay is large field space curvature, which is potentially problematic in fundamental physics and allowed us to conjecture that multi-field inflation in supergravity does seem to be quite difficult to realize. That's all I have to say. So thank you very much for tuning in.